Moving on to I controller now. As explained in the previous video that P controller will not be able to eliminate steady state error for step input for type 0 systems. Suppose consider an I controller where it is E of t dt. It is simply an integration, or in discrete domain it is summation of errors. So for certain values of Kp and Ki at steady state, if we observe, even though the value of error is small at steady state, this integration action will continue to add these small values of steady state error at each sampling instant. Or suppose for some value of for some system with only P controller, if we have such a response, there is a steady state error after certain time, say certain time after 4 seconds. Even at 5th second there is a steady state error, there is a at 6th second there is a steady state error. In P controller, what we are seeing is only E of t. It indicates how far we are from the destination. In I controller, we are adding all these small errors and we are multiplying with Ki. So after some time, if we plug in I controller in this kind of situation, slowly depending upon K value, it will reach the steady state value and the steady state error can become 0. Now this can be proved mathematically by using classical control theory, because the expression for E of S is R of S by 1 plus GSHS. This is known to everybody. So the steady state error as time t tends to infinity is given by this final value theorem. So it depends upon the type of input, that is whether it is impulse, step or ramp, and also it depends upon number of poles at origin of this loop transfer function. So for type 0 system with only P controller, the loop transfer function, there exists a steady state error and that is called positional error constant. So by introducing an integral action into the loop, we are introducing a pole at origin, or we are increasing the type of the system of the loop transfer function. So that means we are deliberately increasing the type of the system. So for type 1 system, for step input, the steady state error is 0. This is the mathematical proof behind this, and this is the some practical intuition behind this integral action. So this completes integral action.